Right, so this is Math331 problem solving lecture 22. Lecture 21B is online. That's the lecture I gave at Swarthmore, where we did Spooner's lemma and saw applications to the Bauer fixed point theorem, which leads to Nash equilibrium. So this was the generalization of, or this was the exploration of the triangle game and the consequences of that. So what I want to do today is I want to do some examples from complex analysis. So let's start with an easier example first, and then we will move up to some more interesting, more involved ones. And so it looks like okay, here is I. So this is the one I want to do first. So I want to integrate dx over 1 plus x squared squared. So this is a somewhat nice function. Let's see, this doesn't seem to want to be turning today, so let's try it. So this is a somewhat nice function. And so the difficulty is always going to be trying to figure out what is the contour and what do we want to choose for the complexification. Most of the time the complexification is not so bad. We'll place x with z. If you have sines or cosines, you want to write sines and cosines as difference or sums of exponentials. And then replace x with z. Because really, what is sine of x? It's an infinite series. We can write it in terms of the exponential function, which is nice. So what would you guess is the function we should look at for this one? What would you choose?
1 plus c squared.
Almost.
1 plus e squared squared.
Almost. 1 over.
Right, yeah.
1 plus z squared squared. So this is essentially just screwing the function we looked at last time. The camera seems to be a little bit, looks like we're drunk. Okay. So this is almost the function we looked at last time. So we know that the poles are at plus or minus I. And what we need to do is we need to figure out what the residues are. We need to figure out the a to the minus 1 terms. Now, the contour we'll use will be this contour. So minus R, not to steal, here's I, here's minus I. So we only need to really worry about what's going on here. So the question is, what's the fastest way to calculate what's going on? Well, we can write f of z as 1 over z minus I squared 1 over z plus I squared. And so now, when we're expanding, we need to find which term over here. We need to find the z minus I term. So how would we get the z minus I term of this? Well, we could play the game we did before. 1 over z plus I, hopefully somebody will remember this. Was it I over 2 or minus I over 2? Minus I over 2? 1 plus z minus I over 2I. I think we had a minus sign here. Let's see. This we can write as z minus I plus 2I. We pull out the 2I. We would have this over 2I plus 1. And then an I down below is the same as a negative I up 2. So I think it was negative I over 2. And then we have a 1 over 2I. And so I think this is now, so does this match what we had last time? Minus I over 2. And then all we have to do now is just expand this out. So let someone check this. So does this match what we had last time? Or did we make an algebra mistake? Or we can do another method and check and see if we've made an algebra mistake.
I think it's negative 1 over 2.
So we have a 1 over 2I. And so if I multiply it by I cubed, so I think it's, does this match what we had before, or if not, let me do it again slowly. So we have z plus I is 2I plus z minus I. We can pull out 2I, we get 1 plus z minus I over 2I. So we get 2I, and then I multiply by I cubed over I cubed, and I'll get 1 down below. I cubed is negative I, so we get 1 minus I over 2 z minus I. And now we want 1 over z plus I, so that should be 1 over 2I. Well, 1 over 2I multiplied by I cubed should become minus I over 2, 1 minus I over 2 z minus I inverse. So that should be what we had last time. That's what I wrote a moment ago.
Why did you multiply?
I'm sorry?
Oh, never mind.
Okay. This is just doing the algebra to write this out. And the important thing to note is if z is very close to I, this quantity here is going to be less than 1 in absolute value. The geometric series expansion will be possible. And all we need is we want the z minus I term. So when we start to expand things, but we're going to have to square things. So the question is, what's the best way to do this? So 1 over z plus I squared is going to be, okay, so I'm going to square minus I over 2. Minus I squared is negative 1, so this should be negative 1/4. And then 1 minus I over 2 z minus I to the minus 2. This is going to be minus 1/4. Now I'll expand this with the geometric series. It's 1 minus I over 2 z minus I plus higher order terms squared. Oh, sorry, that's a plus. Do I need to worry about the higher order terms? So the next term is going to be a z minus I squared, then a z minus I cubed. If I want to find the a to the negative 1, let's look at and see what we have. Over here, I have a 1 over z minus I squared. The way I get a 1 over z minus I is I need the z minus I term over here, because I'm dividing by 2 powers of z minus I. So I only need to figure out the z minus I term here. Okay? So I don't really need anything higher than this. So now I would just square this. And so this would become minus 1/4, and then when I square, I get 1 times 1 is 1. Then I get 1 times this and this times that, so I get the cross term. So I get twice this, so I get plus I, z minus I. And then everything else is going to be a higher order term. So the residue of our function f at I, so we have a minus I over 4 here. So it'll just be minus I over 4. Right, because I'm going to basically divide this by z minus I squared. So the leading term is going to become minus 1/4 z minus I squared, minus I over 4, 1 over z minus I, plus some constant term. So the residue is minus I over 4. So now we go back and we do the integration as before. If I look, what's going on in this big arc up here? Well, it was small before, and I'm squaring things so it's even smaller. So it goes from small to really small, or small to damn small, whatever you want. It's insignificant over the arc. So all that really matters is we get that the integral from minus infinity to infinity, we just take the limit of 1 over 1 plus x squared dx will be 2 pi I times the residue, which is minus I over 4. And we get, this is just pi halves. So whenever you see an answer, you should always ask, is this answer reasonable? So there are 2 checks we can do to see if this answer is reasonable. What's the first check we can do? The simplest check that this answer should pass.
And it's real.
It's real. You can be a little bit stronger than real, but real is good. It's good that it's real. And even better, that it's positive. Right? We're integrating a non-negative function. We should get back, a non-negative number. So this tells us we actually probably to do the expansions correctly with all the i's and the minus signs. There's another test we can do, and this requires you to remember what we did yesterday. Another property this answer should have. So are you surprised that the value is pi over 2? And you can see that pi is probably reasonable because we've got a 1 over 2 pi and I coming in. So maybe I'm not too surprised that there's a pi. Do you remember any integrals that looked a lot like this yesterday?
I mean, we did 1 over 1 plus x squared.
Right, so how should the integral of 1 over 1 plus x squared squared compared to the integral of 1 over 1 plus x squared?
It should be smaller.
Yeah. So it's smaller than the integral of dx over 1 plus x squared minus infinity to infinity. And it should be smaller. Now, the fact that we now square this and we divide the answer by 2, that's probably a coincidence. If we replace the 2 with a 4, it's probably not going to be a 4. Worth checking. I doubt it would be. But. Okay, so this is a way to calculate integrals like this very easily. If you were to try to do this before, you now have to find an antiderivative of 1 over 1 plus x squared squared. That's a hard thing to find the antiderivative. We have converted this problem to algebra. Now, I know a lot of people do not enjoy doing algebra, but when you compare doing algebra to doing painful integration, it's a good trade. It's a trade you want to do. So where was the really hard part? The hard part was trying to find the series expansion. Now, we split our function into two nice parts. This was the part that blew up, and this is the part that was fine. So all we really wanted to do was find the coefficient of the z minus I in this. So maybe there's a better, faster way to do this. So what I want to do is I want to talk to you a little bit about a faster way to find this. And so I will leave the answer on the board. So let's introduce a new function. G of z is 1 over z plus I squared. That's the function we're expanding out over here. And we can write this as an expansion about the point I. So this would be g of I plus g prime at I times z minus I plus g double prime of I over 2 factorial z minus I squared plus dot dot dot. I only need the g prime of I term. And if I had had a 1 over z minus I cubed, I then would have needed g double prime of I over 2 factorial. So let's calculate. What's g prime of z? Well, you take derivatives the same way you would in real analysis. This is, again, a result to prove in complex analysis, but it seems reasonable. So I have this to the negative 2. So we get negative 2 over z plus I cubed. Right? So what's g prime of I? So we'll get negative 2 over 2I cubed. So this is negative 2 over 8I cubed. Well, I multiply by I over I, and the I cubed goes away. And so I will get, and then this becomes now negative I over 4, which is exactly what we got over here, and a much faster way of getting it. So you may feel that this method is a little bit painful because we have to do all this algebra for the Taylor series expansions, but we actually have formulas for Taylor series expansions. And so rather than going through and playing these games with a geometric series and expanding, we can actually just calculate these numbers directly. So it's not that bad of a problem to do. So this is an extremely powerful powerful technique. It's a technique that works very well for a huge variety of problems. Okay, any other questions about this one? We're ready for the more interesting problems? So this is a good chance to ask questions. Yes?
So could you just explain again why don't the higher order terms matter?
Well, because we know we have the following result, that if we have a nice function, the integral, over our closed curve of the sum n goes from minus n to infinity of a n z to the n dz to the 1 over 2 pi I is equal to a to the minus 1. The only term that matters is the a to the minus 1 term. So we had a 1 over z minus I squared. We had a z minus I to the negative 2. So because we have that to a negative 2, we only care about the z minus I to the first power here. If I raised it to the fourth power, then I would have a 1 over z minus I to the fourth, and then I would want to know which term over here. Yeah, the z minus I cubed, which we could find very easily now by just taking g triple prime. And this is actually a very easy function to differentiate.
Why didn't you get rid of this square?
I'm sorry?
It was plus higher order term squared, and then there wasn't a square.
Oh, because I'm expanding it out to get from this line to this line.
Oh, and
What happens when I
okay.
square this? I get 1 times 1,
I see.
then double the cross term. And then whenever 1 hits this or this hits this, that's a higher order term. When this hits itself, it's a higher order term. I only need to keep things up to first power in z minus I. How many of you have taken abstract algebra? I always have to be careful, I can't raise my hand because I've never taken it. Have you done modular congruences, looking at numbers mod 4, mod 5, or looking at things on a clock?
I mean,
Yeah. So I only need to keep track of things modulo z minus I squared. Z minus I squared, I'm essentially considering it to be 0. So when you look at 10 plus 5 on a regular 12-hour clock, you could say 15, but we're more likely to say 3. We don't care about those extra 12s that are accumulating. We can just throw them away. We're just throwing away all the z minus I squares and higher. And that's what makes this technique so nice, is I don't have to worry about that stuff. And in fact, I don't even need to calculate g of I, I don't need to calculate g double prime of I just need g prime of I. Okay, we good on this? Okay, so now, let's go back, and it may take us the rest of the day. I want to do 2 more painful integrals to show you the power of this method. Hopefully you're already convinced, because these are not pleasant integrals to do. The 1 over 1 plus x squared, we could do this with arctangent. And in fact, it's even better, because notice we can only do here from minus infinity to infinity, whereas arctangent, we can actually do from a to b. But if I did 1 plus x to the 4th, 1 plus x to the 6th, 1 plus x to the 5/3, there are ways to do those using complex analysis. Okay. So let's go back to sine of x over x. We will discuss this integral, and then I will debate how much I want to share for my general exam when I was at Princeton about something related to this. So we have sine of x over x dx. So we've talked in the past that this integral is at least well defined. We do have to wait because we have a 0 over 0, but the 0 over 0 is okay. Because when we expand things out, and we're not going to do it with L'Hopital, we talked about that, we get 1. We do have to worry about, does this integral matter how we go to infinity? And I've talked about in the past, if you integrate your x over 1 plus x squared dx, going from, say, minus a to b, if b equals a, you get 0. If b equals 2a, it's converging to the natural log of 2. And the reason is this is an odd function, so if we integrate it from minus a to a, we'll get 0. If we integrate from minus a to 2a, then the integral from a to 2a is essentially integrating 1 over x. When x is large, x over 1 plus x squared for all practical purposes is 1 over x. And that will give you a natural log of 2. So the integral depends on how you go to infinity. This is something that's often not emphasized in your early calculus classes. In the early calculus classes, when you have an indefinite integral, you just compute it. But But you have to be careful and see, does it matter how you go to infinity? If it does, the integral is not said to exist. For the sine of x over x, what's nice is this function alternates positive, negative, positive, negative. So even if we don't integrate symmetrically, we're not going to be missing by much from what the limit are, because it's alternating, and if you have an alternating sequence of decreasing absolute values, that series will converge. So what's going on in the positive tail and what's going on in the negative tail, they both converge. So the integral is well defined. So is everybody comfortable with this? Okay. So the way we did it before, I'm going to erase this very quickly, we shoved it in e to the minus tx. We then said, g of t was the integral from minus infinity to infinity of sine of x over x e to the negative tx dx. We got a g prime of t explicit. We then had g of t was the integral of g prime of t dt plus constant, and that was also explicit. And then we took t equals 0. Once you know to do this, the problem is easy. The difficulty is figuring out what factor do you throw in here so that you can differentiate under the integral sign. So I'm going to show you now how to do this with complex analysis. This one is a little bit tricky with complex analysis. So the first thing is, there are several ways we could do this. We can write sine of z as e to the I z minus e to the minus I z over 2I. The other thing we could do is we could say sine of x is equal to minus I times I sine of x. Not a big deal so far. And then let's study cosine x or cosine z plus I sine z, and that's e to the I z. So we would only have one exponential. I'd love to put in a cosine x over x. What's the integral of cosine x over x?
0.
0. What's the problem with putting in a cosine x over x? So it's an odd function. Why don't I just shove in a cosine of x? So what would be the issue with shoving in a cosine of x up here?
1 over x is not defined.
1 over x is not defined. So the problem is it blows up. So we have two possibilities. One possibility is I can replace sine like this, in which case I'll then have two integrals. I'll have an e to the I z over z, and I'll do that one in the upper half plane. So e to the I z over z we would do like this. And we would have to have some kind of bump over here, because at 0, we unfortunately get 1 over 0. And then e to the minus I z over z we would do down below. So we would have two integrals to do. If I do this change, I only have one integral to do. Well, what I could do is I can do the following. This is the same as the limit as r goes to infinity and epsilon goes to 0, the integral from minus r to minus epsilon, the integral from epsilon to r of minus I cosine x plus I sine of x over x dx. And the reason is now I've avoided the origin where things blow up. In the limit, it's going to converge to what I want. And because cosine of x over x is odd, I've just added 0. So if I do it like this, I can actually do it as one integral and not do it as two integrals. It's worth knowing that there are two different approaches you can do, but given that I'm the one at the board, I'd much rather do one integral than two integrals. So let's do this one. So this is a better way, I think, to handle the problem. Okay, are we all comfortable on that? And so now, we're going to have a little bit of an interesting contour. So our x-axis is no longer going to be solid. We're going to have a little bump that's missing. So it'll go here's minus epsilon, here's minus r, epsilon. I'm not trying to draw this to scale. And then here's our circle. And so there's two ways we can do it. If I do it like this, the pole of the function is outside. And I'm going halfway around, counterclockwise. Or I can go the other way, and I'm going clockwise. I'll do it this way so that there's no pole. We'll just remember how all the things are going. Okay? So we're going to have now essentially four pieces. We have 1, 2, 3, 4. And now we want to, we'll call this curve C epsilon r is the whole thing. And so we'll have 1 over 2 pi I, the integral over C epsilon r of minus I e to the I z over z dz. What does that equal? So what would that equal? Where are the places where we have a pole from e to the I z over z? Where does e to the I z over z blow up?
At z equals 0.
At z equals 0. So how many of the poles are included in the interior of my curve?
0.
0. So what's the sum of the residues?
0.
0, right? This integral is just 0. Now we have to show that the integral over the top arc is insignificant. So let's look on the arc, the big arc. The absolute value of e to the I z over z is going to be times pi r, right? That will be a bound. And I can now write this as, this is going to be less than equal to, well, let's do it for an individual point.
Pi over r.
I'm sorry? I'm going to do it a little slower.
Okay.
This is going to be e to the ix, e to the minus y over r. And this is just going to be e to the minus y over r. So the problem is the length of this is pi r. So when I multiply the bound that works everywhere, when y equals 0, I just lose. Right? So the problem is we need to gain a little bit of decay. Because if I just did the trivial bound, trivially, the contribution is less than equal to e to the 0 over r times pi r, which is 1. And it's not going to 0 with r. But if we just stay a little bit away over here, if we move up just a little bit, so y has any r dependence. Imagine y equals log, 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 from some to build log, 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 r. Then when you exponentiate, you lose 1 log. And you have 1 over log, 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 log. And that's enough to go to 0. So we just need to boost y just a little bit, and then the contribution over this part is negligible. And then we just have to bound this part. Well, if y isn't going up that much, how big do you think this arc is? Insignificant. And then over here, if this arc is really small, I don't care that e to the minus y isn't big. I'm sorry, it could be big. It could be of size 1. Because it's so small, the z in the denominator is enough to have us win. So the question is, how far up do I want to go for y? If y goes up like a log r, that's more than enough. Or maybe even r to a power. How much would I get for the length of this arc? So let's imagine. Let's look. So, this whole thing is r. This whole thing is r. Do you want to try to do a log of r, or do you want to do an r to a power? What are you in the mood for?
R to the power.
R to the power. So let's do r to the delta. We'll give us a free parameter of delta. And then we want to figure out what is, we'll call this angle theta sub delta. What is that angle? And the hope is, well, look, r to the delta, that's going to be really small. So we could calculate maybe the sine of theta delta is opposite over hypotenuse. So the sine of theta delta is r to the delta over r, which is r to the delta minus 1. That's a really small number.
If delta is like.
So this is going to be theta delta minus theta delta cubed over 3 factorial plus theta delta to the 5th over 5 factorial. This over here is going to be, we want to basically just get some kind of upper bound for theta delta. So if I throw away all this stuff over here, I've made the right-hand side larger. And then this would become a lower bound. So if I keep this term over here, I have an upper bound. So this would be greater than or equal to theta delta minus theta delta cubed over 3 factorial. And what you should be able to get from this is theta delta is going to be at most maybe r to the delta minus 1 all divided by 2. What this is saying is maybe it would have been better to use the Taylor series expansion for tangent. And that might have gotten us a better formula. But the point is, you can see theta delta is going to be of size r to the delta minus 1. When theta is small, theta cubed is not going to really matter. Theta cubed will be less than theta delta. So you could probably get that this is going to be greater than or equal to theta delta over 1,000. That's not going to be that bad of a bound to show. And so that means theta delta would be at most 1,000 r to the delta minus 1. So the length of this arc, you then have to multiply by maybe at most 2 pi or pi or something like that to convert from the angle. No, we're working in radians. So that's going to be the angular measurement. So this angle here, this corresponds to an arc here of length at most 1,000 r to the delta minus 1. So we're going to have plenty of decay. Right? Let me just make sure. I just want to make sure that, okay. Yeah. Now I see the mistake I was making. We also have to multiply the angle by r. Right? This arc length is r theta delta, right? Because I'm on a circle of radius r. So that means r theta delta is less than or equal to 1,000 r to the delta. I was just looking at this and I was going, the bound is way too good. So the arc length here is at most 1,000 r to the delta. So I divide by r. Since delta is less than 1, it's insignificant. So the contribution from these little pieces over here is insignificant in the limit. So is everybody comfortable with this? what happens is the more problems like this you do, the more comfortable you get saying, oh yeah, it doesn't matter, it's insignificant. I don't have to move up that much. I'm moving up out of the delta. I could have delta being very close to 1, in which case I'm moving up still a very insignificant amount, because it's a power less. And that's enough so that I now have a little bit of decay in the big part of the arc. And then the parts over here will be insignificant because the arc length is small, and now I get to use the z. So this is a really good problem-solving technique. Break things up into cases. I have e to the I z over z. I have an e to the minus y over r. I break my analysis into two parts. The places where e to the minus y is small, and the places where the arc length is small. And that's how I'm able to win. So is everybody comfortable that the integral over the top is insignificant? The integral over the bottom, this part is going to what we want, and all we're left with doing is integrating this over this little piece. So we're all comfortable that we just have to integrate this. Okay. So one of the problems, of course, is that you can look at this and you can begin to think, maybe that e to the minus t wasn't so bad. The more problems like this you do, the more second nature it becomes and the easier the analysis becomes, and you can just see this is going to be insignificant. I've seen so many things like this that's insignificant. So now we're left with the following. We have this little blip from minus epsilon to epsilon, and we're going like this. So we have the integral, and it's going to be a minus I e to the I z over z dz. So what we can do is we can write this, and I'll call this the semicircle epsilon. And we'll just remember we're going clockwise. So this is the same as the integral over the semicircle of epsilon. I pull out the minus I. And then this is the same as 1 over z, the sum, n goes from 0 to infinity, of I z to the n over n factorial dz. So this is going to be minus I integral over the semicircle of radius epsilon. The first term is 1 over z dz minus I integral over the semicircle of radius epsilon of I to the n z to the n minus 1 over n factorial dz, and I have a sum, n goes from 1 to infinity. And I'm switching the sum and the integral. The point to note now is because n is at least 1, I have a constant term, or a z squared, or z cubed, and I'm integrating over a circle of radius epsilon. So this part here is going to be less equal to, in absolute value, the sum, n goes from 1 to infinity, the integral over the semicircle of radius epsilon of just z to the n minus 1 dz. Well, the absolute value of z is epsilon. And the length of the semicircle is pi epsilon. So this is going to be the sum, n goes from 1 to infinity, of pi epsilon times epsilon to the n minus 1. That's a geometric series. And so this is going to be less than equal to 100 pi epsilon. When epsilon is small. Because I have at least an epsilon term. And in the other one, we'll get like a 1 over 1 minus epsilon. And so as epsilon goes to 0, this is going to go to 0. So the whole point is, the only thing that really matters is the 1 over z term. And so now what do we have? We now have the minus I integral. Now I'm going to write z as epsilon e to the I theta. dz is going to be epsilon e to the I theta I d theta. And what will I get over here? I'll get minus I. I have a 1 over z dz. Ooh, 1 over z dz, the epsilon e to the I thetas cancel. Right? I'll do it slowly. So I have the 1 over z is epsilon e to the I theta. the dz is epsilon e to the I theta, I d theta. And now, what does my theta range from? Theta goes from what to what?
0 to
No.
pi to 0.
Pi to 0. Because we are going things the wrong way. When we have a minus sign, the minus sign allows us to flip the order. Right? So this minus sign flips the order. I times I is -1. These cancel. And we just get negative integral from 0 to pi of d theta. One of the best known integrals of all time, when integrating a constant. So we just get minus pi. So putting all of our pieces together, this whole integral is going to lead to this piece plus this piece plus this piece plus this piece plus this piece equals 0. So since these all go to 0 in the limit, it's just this plus this equals 0. So this equals negative that. So this is just equal to pi. And so when you put all the pieces together, we get that this is just equal to pi, which is what we got before. So it looks worse than it is. It follows using our standard result from complex analysis. Part of it is we just proved a new result. That new result should be isolated as a lemma. If you integrate 1 over z over a semicircle of radius epsilon, you basically just get half the contribution. And if you notice, we're getting pi and not 2 pi. Okay. Any questions about this? All right, so I will share now a problem for my general exam. So for my general exam, the way they do the exams at Princeton, I'll be very careful because this is being recorded, is everybody takes real, complex, and abstract, and you choose 2 special topics. You should always think about what problems you might want to do, if there's an order you want to do things. And in the complex analysis part of the section, they gave me the integral from -infinity to infinity of sine squared of x over x squared dx.
Can you just,
Yes?
or could you do something with sine squared of x plus cosine squared of x equals 1?
Well, the problem is, if you do, then you'd be integrating 1 over x squared, and 1 over x squared blows up.
Right, but you could do the little like epsilon limit thing.
So you could do the epsilon limit thing, but now when you put in cosine squared, the integral of cosine squared of x is not the same as the integral of sine squared of x. If you were just integrating sine squared and cosine squared over periods of length 2 pi, it's the same. But it now matters because they're weighted by 1 over x squared. How could you solve a problem like this? What could you do? Based on what we've learned today, how might you attack this? Should be able to give you 2 ways you can attack this based on what we've done today. Yes?
Maybe sub sine squared of x as e to the 2iz minus, or like you can call it sine squared of z, and then you could say e to the iz.
So square sine of z.
Square sine of z, yeah.
So one possibility is sine squared of z is e to the iz minus e to the minus iz all over 2I squared. Now when you square it, you'll get an e to the 2iz, you'll get an e to the minus 2iz, and you'll also now get a cross term. Oh crap, that's just a constant. Well, we can deal with that. So you'll have 3 terms to deal with. That's solution 1. Solution 2, could we try to do the trick with with writing your sine as like minus I sine, and then putting in the cosine? No, that's not going to work now. There is another way to attack this. What other integration techniques do we have going all the way back to when you were in high school? We should probably be able to do it. What's your favorite technique of integration other than your substitution? Come on, other than use substitution.
Parts.
Integrate by parts. So you need to choose what do you want u to be, what do you want dv. Do you want u to be 1 over x squared, in which case you'll have a higher power of x, or do you want dv to be 1 over x squared, so you would get a lower power of x? Not that I'm trying to influence you at all.
dv is 1 over x squared.
Excellent choice. And then u is sine squared of x. du is 2 sine of x cosine of x. And what's b? Negative 1 over x dx. The boundary terms will vanish in the limit. When I have uv, the boundary terms vanish. And I get that this integral is equal from minus infinity to infinity. The negatives reinforce, and I get 2 sine of x cosine of x over x dx. Life is good if you remember things. What should you remember right now?
Why did the negatives cancel?
Oh, because it's uv minus v du.
Okay, minus.
Minus v du. So what should you remember right now when you see this numerator? This is sine 2x. So I'm integrating minus infinity to infinity of sine of 2x. What should I do now? How do I pull out a 2?
Put a 2.
Yeah, put a 2 down here, put a 2 down here, and then just change variables. U equals 2x. This integral is the integral we already did. So if you actually integrate by parts, you can reduce the sine of x over x squared to the sine of x over x, which we know how to do, and in fact, which you can do using real analysis. So, I don't have enough time to be a little bit of a smart ass. So when I had this as a general exam question, I remember when I was taking complex analysis in college, I remember doing this. And in fact, I had just looked at that the night before my general exam. And I asked the professors, do I have to use complex analysis to solve this, or can I convert this to a real analysis problem? I said, oh no, by all means do whatever you want, as long as you can solve it. So I converted it to sine of x over x. And then they rolled up their sleeves and said, okay, let's now consider generalizations of this. And they gave me generalizations of the Fourier transform, which was a lot of fun. And the whole point of this is, if you can get the examining committee to be having fun, and you can have fun, it's a lot better. And they had no problem with my bypassing the complex analysis and moving to the fine. We can work in the complex analysis by giving you generalizations of the Fourier transform, which we'll see what goes on. But it's interesting to look at whenever you have something like this. Before you try doing some very painful things, is there a way to simplify it and reduce it to something you've seen before? So this is nice because it mixes various techniques. It mixes the integration by parts with what we're doing. All right, so next class we will do the Gaussian integral. And there is a way to do the Gaussian integral. This is the one we did with polar coordinates using complex analysis. It's a little bit tricky because there's no poles. And so we need to find a way to shove poles into the function. And so it's a nice technique. So that'll probably be it for the complex analysis techniques.